Hello, everybody. My name is Shangyang Li, and welcome to join us for today's OTFS SIG online seminar. Today, we are very glad to have Dr. Ali Bemani from Huawei, France, to give us a presentation on AFDM. So this online seminar has been organized by me and Wei Jie, Zhiqiang, Han Tang, and Yi Gong. If you are interested in knowing more about this OTFS or in general various waveforms, please, you are more than welcome to join our special interest group. And these are some details, and these are the mailing list and the SIG websites. So without further ado, I'm going to introduce briefly about our topic today. It's AFDM, Affine Frequency Division Multiplexing for various communications and ISAC, and is going to be presented by Dr. Ali, by Dr. Ali Bemani. So Dr. Ali received his bachelor degree in electronic engineering from Amikra University of Technology, Iran in 2015, and he has received his master degree in communication systems from Sharif University of Technology, Iran in 2017. He received the PhD degree from Eurocom, Sorbonne University, France, in 2023, where he proposed the AFDM as a new chirp-based waveform. Since October 2022, he has been a researcher at the Mathematics and Algorithmic Science Laboratory, Huawei, France, Research and Development, France. His research interests include wireless communications, waveform and reference signal design, channel estimation, and integrated sensing and communications. Okay, so please join me to welcome Dr. Ali for today's presentation.
Thank you, Shuanggang, for the introduction, also for the invitation. And also I wanted to thank you for organizing such talks. It's really helpful and good for our community to get more familiar with the new topics and the waveform design. So now I'm going to share my slides. Okay. So I think now you see my slides, right?
Yes, it's very good. Thank you.
So yeah, as Shuanggang said, the topic today is about AFDM, so which stands for Affine Frequency Division Multiplexing for wireless communication. So the talk is about AFDM for wireless communication and ISAC. This talk is by me, Ali Bemani, Wisal Benzen, and Nasser Kosari. We are here in Huawei, Paris, working on different topics on waveform design, including AFDM topics. So in this talk, first, I'm going to give an introduction about why we need a new waveform. I think it's everybody almost know about it, but I will do that. And then I will talk about Affine Fourier Transform, which is the backbone of the AFDM. Then I will go for the AFDM principles and how AFDM achieve the full diversity of the LTV channels. And after that, I will talk how AFDM also could be applied for the sparse channels. And then I will talk about applications. Here I will mention two applications, how AFDM could be used for the monostatic radar, and also how it could be used for the sub-Nyquist radar. And then I will, as a further topic, I will show the other people who are working on AFDM for the low PAPR AFDM. So we all know that the waveform design is the major change between the generations. So from the first generation that AFDMA was the case for the waveform until the fifth generation, while OFDM is working there. So now the question is that what would be the options for the next generations? So because we know that for the new generations, we would have new use cases. We would go for we would have high mobility scenarios. We would have high frequency bands. So then this next generation wireless standard should support this kind of use cases. And another thing, we know that so far OFDM was playing the role for the waveform in the 4G and 5G, but we know that OFDM is designed for the LTI channels. And when we have Doppler spread when we are in the high mobility scenarios. OFDM have some problems. The problem is that in the doubly dispersive channels, or i.e. LTV channels, OFDM loses orthogonality among different subcarriers, so which leads to intercarrier interference, as we can see from these two figures, and then it loses its property. So now the question is that what we need in general for LTV channels, and on the other hand, we know that the optimal approach for any channel is to find its orthogonal eigenfunctions, which is restricted to that channel. And then using that eigenfunctions, we should modulate the information, and at the receiver, using the same eigenfunctions, we project the received data over that eigenfunctions and then do the modulation. So this is a straightforward for the LTI channels, because the complex exponentials are the eigenfunctions of the LTI channels, and this could be harnessed by using the Fourier transform. But in general, for LTV channels, finding the orthonormal basis is not as straightforward. It's like conceptually and also computationally, it is complex. So what we came up to use is like, what if we go for the chirps and form an orthonormal basis using chirps? By chirps, I mean complex exponential with linear frequency modulations instead of sinusoids. So I will show during this presentation that how these orthonormal bases could be adjusted to the channel, and I will explain what do I mean by adjustment to the channel. So before going to the AFDM principle, first we can quickly look at the affine Fourier transform. So affine Fourier transform is a general transform that generalizes many standard transforms, such as Fourier transform, Laplace transform, fractional Fourier transform, or other known transform as well. So it has 4 parameters, like as we can see in these slides here, like A, B, C, D, and also it has 1 constant. So we have 3 degrees of freedom, and according to the value that we are giving to these parameters, we could have different transforms. And in general, like A, B, C, D, they could take any arbitrary values. We should just respect this constraint. So it also can have a discrete version, but there is no one unique discrete version for the affine Fourier transform. One possible discretization of the affine Fourier transform is proposed by Estraga in 2005, which it has 2 parameters, C1 and C2. And also it can have a parameter here for the frequency component here, but we don't consider it. So we have 2 parameters, C1 and C2. And if we want to write it in the matrix form, it would be the generalization of the Fourier transform matrix. So if we have, for the Fourier transform matrix, we know how we have this F matrix with these elements. So for the DAFT matrix, it has 2 other diagonal matrices. Lambda C1 here, we denoted them with lambda C1 and lambda C2. So this A matrix could be considered as a DAFT matrix. And another thing I wanted to mention here is that since so for this transform, we don't have the normal periodicity. We have some kind of periodicity that we call it chirp periodicity. As we can see here, if we go from n sample to another n sample, they are not just repeating. So we have this term as well. This term then multiplied by the signal. So this is why we call it chirp periodic. And the reason we should take this matter to account that when we wanna send our signal over the channel, this is for any signal that we need to extend it because we wanna avoid ISI. So as for OFDM, we have a cyclic prefix. Here, in general case, we cannot have cyclic prefix because of this special periodicity that we have. So if now we go for the AFDM principle, so the signal that we want to modulate is using the IDAFT, as like for OFDM, which use IFFT. Here, if you look at in this figure, we can see that this is the generalization of the OFDM, so that we have two more blocks than IFFT, lambda C2 and lambda C1, and most of the features of the AFDM comes from this C1. That if we look at, so if we modulate the symbols using this, now we call it IDAFT module, we can see that the time frequency representation of the channel would be something like this. So we know that for OFDM, each subcarrier would have a fixed frequency, but here it's different. Yeah. And the reason is that it's because of this chirping we are doing here. So we can see that for each subcarrier, we have a chirp, or we can call it a sub-chirp. And the slope of this chirp depends on the C1. So the larger the C1, the larger the slope of this chirp would be. And as you can see here, we would have, instead of CP, we call it CPP, which stands for chirp periodic prefix. As I said, it's because we don't have the normal periodicity, but this is for the general cases. If we go for if 2 and C1 is integer and the n is even, then CPP is simply a CP. But we should be careful about it, because it's not always the case. But for the cases that we are considering, from now on, CPP is a CP. And the channel that we are considering for AFDM is a doubly dispersive channel. As I said, the reason that we went for the AFDM is that we wanted to deal with the LTV channel. So here is the channel that we are considering. So we have a multi-pass channel, and each pass has its own delay and Doppler shift. And we know that in the practical cases, we can have fractional delay and also fractional Doppler case. We also investigated the effect of this. We will show as well in the slides that how this fractional delay and fractional Doppler would affect the input-output relation. So if we have a large bandwidth or large duration, then maybe this fractional part, the effect of this fractional parts does not matter that much. But in general, we should take the effect of fractional parts either for delay or Doppler shift into account. So now that we define the channel, we can look at the input-output relation. I didn't bring the details, because especially when we have the fractional delay, it would be a bit complicated. And maybe I just, inside the parentheses, I would explain about why it is a bit difficult for, a bit different, I would say different for the fractional delay. Because if we want to go for the fractional delay and see the effect of fractional delay, first we should go for the continuous version of the signal at time domain. So we should oversample the signal, or we should go for the continuous domain. And for the AFDM, if we want to go for the continuous domain, yeah, it is a bit different. We would have two cases. One is like we can go for the continuous domain by going to the frequency domain and FFT and IFFT, and then we are in the continuous domain. But it would be a bit difficult to find the input-output relation. Another thing is that we can just write the continuous version of the discrete chirp. But one thing we should take into account is that I want to mention here is that because I saw in some papers it is not respected that much. So if we look, for example, in the subcarrier M, we see that after it reaches the bandwidth, it comes to the zero frequency. But if we just put N to T here, it is not the case for the continuous domain. So we need a modulo operation, and then it should be taken into account. So be careful about this. I just wanted to mention here. And then this after all of this, we would have the input-output relation, and it depends if we have the fractional delay or not, or fractional Doppler or not. It would be a bit different. Here I will graphically I will show the input-output relation, for example, for a 3-pass channel. So if you don't have integer, so in these figures we have integer delay, and we have integer Doppler or fractional Doppler. We can see that if we have integer Doppler shift for each pass, we have only one non-zero element in each row or column of the effective matrix. But if we have a fractional Doppler shift, instead of one non-zero element, we would have a spectrum around this main subdiagonal. So, and but one thing also I should mention here is that theoretically, we would not have a spectrum. All of the this row or column would be non-zero. But when we go away from the peak, it reduces significantly. So that we just take the k nu or 2k nu significant values. After that, they can be they are negligible. And another thing for the input-output relation is that so one is that if we have integer or fractional Doppler, we would have a spectrum or not. And another thing is the location of this spectrum. As we can see in the figure A, the pass 1 and 2 they are overlapping, but in pass B they are not overlapping. And this the location of these diagonals depends on the C1. So now we can see that what would be the effect of C1 in the input-output relation. And so since we are going for AFDM, we want the full delay-Doppler representation of the channel. So we want the AFDM, we want an input-output relation for AFDM so that all the passes are separated from each other, so that we can have the full delay-Doppler representation. And in the next slide, I will show that if we can have the full delay-Doppler representations, first we can prove that we would have the full diversity of the channel. And in the next slides, I will show that the channel estimation, also the amount of the sensing, can be handled very easily by the AFDM as well. So the condition here, so now with this thing that I said, in order to have the full delay-Doppler representation of the channel, the intersection of the ranges in the input-output relation for each passes should be zero, should be empty. So this leaves us with this C1. So it means that C1 here, the K max is the maximum Doppler shift of the channel, and K nu, as I explained, is due to the fractional Doppler. So if we don't have fractional Doppler in some scenarios, then this K nu could be zero. And the K max is the maximum Doppler shift of the channel. So in this way, it is adjusted to the channel. So, and as I said, as I showed before that, we can see the effect of the C1 here, which is the slope of the chirp, which is not the case. For example, for OFDM, we don't have any chirping. For OCDM, it is fixed, which is C1 is always 1 over 2n. But AFDM, we can tune the C1 in a way that it would be adjusted to the channel, to the LTV channel. So with this C1, now we can see that we would have the full delay-Doppler representation of the channel. This is the effective channel matrix. We can see that for each row, and also this would be the case for each column as well, that we can have the full delay-Doppler representation for each pass. So for example, in one example, if we have a non-zero element here, it means that we would have a pass with a delay I, and its Doppler shift is this value, for example, k prime max -1. So in this case, all the delay and the Doppler component of the channel could be seen in this effective matrix. And another thing I wanted to mention here quickly is that its relation with the Zag transform. So There is a good paper for the chirp, discrete chirp, the Zag transform of the discrete chirp, and in this paper they are investigating the Zag transform of the discrete chirp, and they have different theorems so that what would be the condition of the discrete chirp so that the Zag transform of this discrete chirp has a finite support. So and if we look at the AFDM chirps under the assumptions of this paper, we could see that the AFDM chirps, the Zag transform of the AFDM chirps also has a finite support. This is another way to show that with the AFDM chirps, we can have also the full delay-Doppler representation of the channel. And here we can see, here we show one example for the Zag transform of chirp. So here C1 C2 is equal to 1 over 2k, where k is the length of the vector here, and m Zag is equal to 2n Zag, and we can see that here the Zag transform of this chirp has a finite support. And also if we send a chirp over the channel, and again we can show that the Zag transform of the output of the LTV channel when we are sending an AFDM chirp, we also have the full delay-Doppler representation of channel. For example, here we have, just for the sake of simplicity, we have integer delay and Doppler shift, and each channel has the delay of so we have the delay of 0 and 1, and for each delay we have the Doppler shift of -1, 0, and 1. We could see from this figure that we have only non-zero element for these delays. So the delays and the Dopplers could be abstracted from the Zag transform of the chirp as well. This was another explanation for the AFDM as well, because the people in the community, I think, because also the people who are working with OTFS are familiar with the Zag transform. So that said, now we can show that the AFDM can achieve the full diversity of the LTV channels. So so if we look at again the input-output relation, and we write it in a way that we have this phi matrix, which take into account the different matrices from different passes, H1 to HP, and then we look at the pairwise error probability, we can define the diversity order as the minimum rank of this matrix when we are considering every possible error vectors. So if we go into the details of this and look at the rank of this matrix, we would have two conditions for this matrix to be full rank. The necessary condition is that the passes should be separated from each other. As I explained earlier, it is the case for the AFDM. For example, this is not the case for the OCDM in the LTV channel, while it is the case for OCDM for the LTI. So in the LTI channel OCDM, the passes are separated from each other, but in the LTV channel, it's not the case. But this is the case always for the AFDM if it tunes C1 in the way that I explained. And the sufficient condition is this expression. So why we have this expression? It depends on the maximum Doppler shift and the maximum delay. And the reason is that, so assume that we have a very large delay. So in this case, as I showed the effective matrix, the last delay would come to the first delay due to the modulo operation. So for example, if I show here, so for example, if we have a very large delay, this L max would come here and then come here, and then it cannot be here, so it comes here, and then two passes have overlapping with each other. That's why we have this condition as well. And then if these two conditions set, then with setting C2 to be either an arbitrary irrational number or rational number if sufficiently smaller than 1 over 2n, we can prove that, and we proved it in our article, that it achieves the full diversity of the channel. And now just to show that it also achieves the full diversity of channel. Here we have the n is really the number of subcarriers for the AFDM is really small, because we wanted to do the ML detection, just showing that it achieves the full diversity of the channel. We can see that for if we increase the number of passes, the slopes in the highest SNRs is equal to the it shows that it achieves the full diversity. And here we are comparing it to the other waveforms like OFDM, OCDM, OTFS, and we see that also with the ML detection, AFDM and OTFS also has the same performance, while OFDM and OCDM has worse performance. So, and also another thing is I want to mention about the OTFS, because there is a paper saying that the OTFS theoretically doesn't achieve the full diversity of the LTV channels, but it's at very high SNRs. And then there are another papers saying that it's in the like reasonable SNR, it achieves the effective, effective diversity of the channels. So we can see that they have almost the same performance. So now we can talk about the channel estimation, how the channel estimation can be done for the AFDM using the fact that it has the full delay-Doppler representation of the channel. So actually there are a lot of papers out there for AFDM, for channel estimation for AFDM. But here I don't go into the details of the algorithms for the channel estimation. I would show only how we can do the channel estimation for AFDM with only one pilot. And then I will mention a couple of papers for the different algorithms for AFDM. So the signal model that we are considering for the AFDM is as follows. As we can see from this figure, we put one pilot, and the location doesn't matter, and then we would have guards, and also then we would have data. So in this case, we can do the data detection and channel estimation within the same AFDM frame. And so the length of this guard interval depends on the maximum delay and the maximum Doppler shift. And since we have these guard intervals, we can boost the power of the pilot here without resulting in an increase in the average transmit power, because we have some zeros here. So now that we have, if we send this signal at the receiver, since we have the full delay Doppler representation of channel, we know that this pilot would result to this part of the signal, and that the rest are only related to the data. So for the channel estimation, we should look at only this part of the signal, which reduces the size of the signal, and it reduces the complexity as well for the channel estimation. And also, like if you go here, you can see the details, like this blue part. Only since we are sending only one pilot symbol here, then we should, it is as if we are looking at the one column of the effective matrix. So, but as I said, each column or each row of the matrix, effective matrix, has the full information of the channel, so we can estimate the delay and also the Doppler components of the channel. And also, so the algorithm that we are using is the approximated. So first we use the ML estimation, and then by some approximation we are solving it. So here we can see that if we have enough SNR for this pilot symbol, we can almost have the same performance of the ideal channel when we are computing the bit error rate. But one thing we should take into account is that this SNR also translates to the overhead, because if we want to increase the SNR of the pilot, we should put more guards so that we can boost the power of the pilot, and we should take into account this thing as well. Now, if we compare this embedded pilot channel estimation for different waveforms, again, if we look at the bit error rate, OTFS and AFDM has almost the same performance, but better than the OCDM and OFDM. But if we consider also the spectral efficiency, AFDM has a bit better performance, and it's because of the number of guards we need to put for these two waveforms are different. So if we look at this figure, actually the number of guards that we need for the OTFS is almost 2 times more than the ones are needed for the AFDM. And the reason is that so if we reshape the AF, because the AFDM SIG vector, we have a vector for AFDM, it's not a 2D transmission, but if we reshape it in 2D and then we compare it with the OTFS, here the orange and the purple color are common for OTFS and the AFDM. These all colors are for the guards. So, and the channel estimation would be done here with using this purple color. But for OTFS, the red one, the red color here is the excess overhead with respect to the AFDM. And the reason is that for the OTFS, we have Doppler in each column. So we should respect it in the upper part and below part. But for AFDM, since it is a 1D signal, the delays and the Dopplers are twisted. So that's why we have this gain here for the AFDM. So these are the other papers also for the estimation for the AFDM. So you can see that actually there are more, but I just put these papers which has different algorithms like message passing, Bayesian parameter bilinear Gaussian belief propagation, or superimposed pilots, which also there are a lot of papers for the channel estimation for OTFS as well. But I just what I want to mention here is that the comparison I did is like when we want to do the channel estimation for AFDM and OTFS, when we don't want the data and the pilot interfere with each other. So now also, so far what I explained is that when we don't have any when we don't have any assumption for the sparsity of the channel. So if we have a sparsity, I will show that we can go for a smaller C1, because the larger the C1, the larger the overhead we have. So, but if we have a sparsity, maybe we don't need to go for the very large C1s. So for that, the assumption that we have here is that we consider this channel and we consider two-dimensional Bernoulli Gaussian distribution for the channels. Meaning that if this ILQ is Bernoulli, it has a Bernoulli distribution, and when it is E1, the channel is active, and when it is not, when it is 0, it means that we don't have any channel there. So here we can consider a doubly. We can assume that we have a doubly sparse channel, meaning that we have a sparsity for the delay and the Doppler. So this ILQ could be written as IL multiplied by IQL, which both have Bernoulli distributions. And we can take 3 different types for this distribution. First of all, if you look at type A, it means that we have a distribution for the delay, and within each delay, the distribution for the Doppler is random, but the same for all of the delays. So here, the IQL, we don't have the index L, doesn't matter. We have IQ for all the delays. This would be one type. Another type is that everything is random, so we have this randomness for the delay. Also, we have the randomness for the Doppler, so we don't have any. The clusters for the Doppler also is random. And for the type C, which is the most practical one, is that we have randomness in the delay. Also, we have the randomness in the Doppler, but the spectrum is almost the same for the Doppler of each delay. But we can prove the things that I'm showing next in the next slide for all of these three types of assumption that we have. So in this case, when we have a sparsity, we show that we can go for a small C1, but instead of using one pilot, we can use NP pilot. And now we should look how many pilots we need if we want to go for a smaller C1. So if we look at this blue parts in the received signal, so YP, it would be equal to MP, which is the measure, we call it the measurement matrix, multiplied by alpha plus noise. Alpha here is a doubly sparse because, as I said, we have the doubly sparsity in the delay and the Doppler. And this problem is a hierarchical sparse recovery problem. And for such problems, we should look at the high rip constant of the measurement matrix because it is an important performance indicator. And here you can see the definition of this constant, which denoted by this, denoted by delta, and so this high rip constant is the smallest delta that satisfies this equation for all of the SN, SM, sparse vectors. And these vectors, so it means that this SN, SM sparse vector, what are they? They are this. So if we have a vector and then we reshape it in the N, like if, for example, we reshape it in N columns and M vectors, it means that out of M in each row, out of M components, there are SM non-zero elements. And in each column, out of N elements, there are Sn non-zero elements. So since we consider the Bernoulli distribution, we can say that with a very high probability, also we have this kind of thing for this alpha vector. It means that maybe if I come back here, if we should multiply this row D by the maximum delay L here, we assume that it is a very large number, then we can have the number of non-zero elements in the delay and also the same for the Doppler when we multiply this row capital D by the 2Q plus 1, because we have 2Q plus 1 in general, the Dopplers, but most of them are 0. So if we take to account all of these assumptions, we would have this theorem. I know it is very technical here. If you need to go to the details, this is the work of Vishal. You can also feel free to ask her if you have any questions. But the takeaway from this theorem is that the number of pilots is here. The number of pilots grows logarithmically with the maximum, with respect to the maximum delay L here and the maximum Doppler shift Q. So if we have a very large L and Q, we don't need a lot of pilots. This is the takeaway from this work. And the idea of the proof, if I just want to mention it, is that for the measurement matrix MP, computing its high rip constant is very difficult. So what we do instead, we find an equivalent hierarchical sensing problem with Kronecker measurement matrix, which involves a partial Fourier matrix whose rip constant can be derived from the known results, as I mentioned them here. So if you're interested in this work, you can look at the paper itself, also these results. So that in this case, AFDM also can be used for the sparse channels, while we don't go for this large C1, which is needed for the full diversity AFDM. But we, instead of one pilot, we use a couple of more pilots, but the number of pilots is not it grows logarithmically with respect to the maximum delay and also maximum Doppler shift. So now I will talk about the applications of the AFDM. So one application is the monostatic radars. We know that nowadays ISAC is gained a lot of attention due to its benefits in terms of lower power consumption, improve the spectral efficiency, and also reduce hardware costs. And we know that for the radar, we should estimate the delay and Doppler components of the identifiable passes. And this aligns with the principle of the AFDM, because AFDM also has the full delay Doppler representation of the channel. So for first, we can go for the monostatic radar, as we can see from this figure. Actually, this is a communication transceiver, sorry. So we would have ISAC signal, we would have echo from the targets, and also for the monostatic radar, we have the self-interference signal as well, which is an order of magnitude larger, and we should see how we can behave this signal as well. So the signal model that we are considering is actually for the system model. So we consider P point targets. Also, we have another passes, which is the zero passes with the zero delay and zero Doppler shift, and is the, as I said, is the self-interference pass. So, and we should see how we can behave this signal. And at the radar receiver, we have two options. Either we can go for the whole signal, because at the end we know the signal at the receiver, because the receiver and the transmitter are in the same place. We know the signal, and we can do the detection based on the whole signal or the pilot part of the signal. So two things we show. One is that if we do the sensing based on the pilot part, the performance is almost the same as when we do sensing with the whole signal, because as I showed, we have all the information of the channel also in that part of the signal which is related with pilot. But if we go for the pilot part, we have another feature, and the feature is that we can have a very simple self-interference cancellation method, because the AFDM has a chirp nature, and using this chirp nature, we can come up with a simple self-interference cancellation method. And because we know that with this, when we have this self-interference signal, it demands for a very large dynamic range for the ADC. And that's why we need to remove the effect of the self-interference signal before the ADC. So let's see how this could be done in the AFDM system. So assume that, first of all, let's see how analog dechirping works for the AFDM. Assume that we have two chirps, as we can see in this figure, chirp M1, chirp M1. If we do analog dechirping with the M0 chirp, we can see that when we do analog dechirping, the result, so when we do analog dechirping with the M0 chirp, for the M0 chirp, the result would be here at the zero frequency. So it's the green one. And for this chirp, the red one chirp, M1 chirp, the result would be here at the frequency of M1 minus M0, and here as well. So now let's come back to the AFDM ISAC receiver. So at the receiver, we would receive the self-interference signal, which is this black one. Also the echoes from the other signal, which are order of magnitude smaller than this signal around this self-interference signal. Also, we would receive the data parts here. So assume that the red one is the data part, the echoes are around this black one. And then we do the analog dechirping with the M0 chirp as a reference chirp. When we do it, so the self-interference signal would appear at the zero frequency, the green part. The echoes would be around this zero frequency, and the length of this desired, we can call it the desired bandwidth, is depending on the maximum delay and Doppler shift that we want to have. And the red one are the effect of the data signals. So they are far from the desired parts because we have guards between the data and the pilot. So now how we can remove the effect of the self-interference cancellation. So we see it is in zero frequency. So with the DC blocking module, we can remove the effect of the self-interference signal. And if since the data part and the desired part are separated from each other, so if we take out the desired parts, the orange parts, by a filter, then we have the self-interference free signal, so we can do the detection according to this signal. And another thing we see here, this discontinuity in the red signal, or also we have it for the echoes as well, would disappear because when we go to the digital domain, we have this aliasing. We call it proper aliasing. And then it actually doesn't make any problem for us, this part. And so here we can see the block diagram of the receiver for the monostatic radar. So as I said, we do an analog dechirping with the reference signal, and then we have a DC blocking module with filter, and then here the signal is interference-free signal, and then we do the FFDM. We can do the target detection. So thing is that this is an advantage over like OFDM and OTFS based ISAC schemes, because for them we need full duplex method to remove the effect of the self-interference signal. And if I show the simulation results here first, in this figure we compare the two schemes. One is when we do sensing with the full signal, and when we do sensing with the pilot only signal. So we can see that the performance is almost the same. We have the saturation because of the resolution, so we cannot go beyond the resolution if we don't do super resolution methods. And by pilot overhead, so if we increase the overhead, it means that we can boost the power of the pilot, like I said about for the channel estimation. And then we can see that it improves a bit the performance, but in general the gap is not that much. And so I think the gain is more important for us, so we can have this gap, but with the simple self-interference cancellation methods. And here we are comparing with the OTFS and OCDM. We can see that almost again we have almost the same performance, but the self-interference cancellation methods are different for these figures. For OTFS, we need full duplex. For OCDM, although we can have this analog dechirping, because OCDM also has it is a chirp signal. But since we cannot even see one, we cannot sense the environment with only one pilot. We need multiple pilots depending on the depending on the maximum delay and Doppler shift. And for each pilot, we need an RF chain. So for example, in this example, we need 5 RF chain. But for AFDM, we need 1 RF chain as well. 1 RF chain. The second application here I want to mention is how AFDM can be used for sub-Nyquist radar. So, sorry. So, if we can prove that if we downsample an endpoint AFDM chirp by a factor of O, so for this this long AFDM, the chirp rate is C1. Then the resulted signal, as we can see from this figure, is it gives us another chirp actually, with which its length is n over O, because we are downsampling the received signal by the factor of O, and its chirp rate is increased, as we can see here. I mean, if you compare it in a discrete way, its chirp rate is increased, and it is equal to O squared C1. And here we can see the proof in the mathematical way. And it doesn't matter where from which subcarrier the chirp starts, like if M. So, but we have different kind of rules after the downsampling. Here the M is equal to M, but we have a modulo operation here because the M is larger than the bandwidth over O. So when we do the downsampling here, we see that we have another chirp with a different chirp rate with a smaller length, but also the bandwidth also is divided by O. But if we know that if we want to do the sensing for the range, the bandwidth is it play an important role here. So we don't want to lose in the resolution. So if we look at the downsample signal, AFDM signal, we can show that actually we don't lose in resolution, although we are going for the downsample version. And here, by the way, I should say that this is only if we want to have range estimation only. We don't go for Doppler in this case. So here, if, for example, if we want to show this, that we don't lose in resolution. So as an example, take X, we are sending X, and X is AFDM chirp. And then the channel has a discrete delay of 1. I mean, 1 over bandwidth seconds. So Y would be, if the CPP is CP, then the Y is simply the circular reshifting of X. So as we can see here. So this would be Y. And then when we do the downsampling Y, the received signal Y by O, we at the end we have this signal. So if we look at this signal, we see that up to this phase rotation, which we don't care here, this signal is another chirp. The chirp rate is C1 O squared, and we have a frequency shift here. While we didn't have frequency shift, we have a delay shift here, but here we have a frequency shift. So it means that the downsample signal Y up to a phase rotation is equivalent to frequency shifting NO long linear chirp with a chirp rate which is O squared C1. So because as I said, look at this one as a NO long linear chirp with a frequency shift. And the frequency shift is equal to M minus 2NC1 with this modulo operation. So it turns out that the delay appears as a frequency shift in the downsample version, and we don't lose in when we do the range estimation. We can do the estimation without losing in resolution. And the thing, how it works, the thing is that it works because if we look at the delay-Doppler representation that I showed for the effective channel, we saw that for each delay, we have a spectrum for the Doppler. So when we don't have Doppler, this spectrum could be used for the delays. So since we are in the downsample version, the C1 is increased. We have some more spectrum for the Doppler, but these Dopplers are used for the delay estimation. So that's why we can use it and we don't lose in the estimation resolution. But another thing is here we should mention is that we also, obviously, when we do this, we lose in the maximum range. So the maximum range that we can estimate it would be divided by O as well. So this is what I explained. So the signal the downsample version of X and Y are distinguished as long as this M minus 2 and C1 is non-zero. And so for that case, we can tune O and C1 in a way that this condition would be guaranteed to be satisfied. So then it means that at the receiver, we can do the sampling by the rate bandwidth over O instead of bandwidth, and still two delayed tabs that are separated only by bandwidths are distinguishable. As we can see from this figure, the red one, the orange one, is the sub-Nyquist sampling with factor of O, but still we can see that the delays here is like with the fractional part, and these are 20 and 2022, and these are two. I just put 20 and 22 because otherwise we couldn't see two peaks. They are close to each other, but we can see that we are keeping the resolution. Also, we went for a downsampling with factor of 4 here. And as the last slide, I just want to show a further topic, which is low PIPR AFDM. So there are a couple of papers out there. I just mentioned two of them here. One is DAFT spread AFDM, which takes the idea of the DFT as OFDM, but instead of DFT, we are using DAFT transform. Actually, we have a patent on that as well, so it's really decreases the PIPR, and also we can multiplex users in this case as well. And also another paper, the idea in this paper is that because so far we didn't talk about C2 that much, only for the proof of the diversity analysis. But the idea in this paper is that instead of one C2, we can use different C2 for different subcarriers and tune them in a way to decrease the PIPR. Actually, it decreases the PIPR, but it is complex because it depends on the data. But the idea was good, and I mentioned it. And that's it from my side. Thank you for your attention. And these are the papers that this talk are based on. So if you want to have a look on this paper, you can take a screenshot if you want. And yeah, that's it from my side. Thank you for your attention.
Thank you, Ali, for the great presentation. And it is indeed very informative and quite enlightening. We have collected several questions from the audience and also some of myself. I would like to organize all these Q&A sections into different sectors because this presentation is actually quite broad. People are asking different aspects. So I would like to start with the parameter selection, which is actually in terms of the first few slides in your presentation. So you have mentioned some differences between AFDM and other waveforms, and particularly the parameters. For example, on page 10, I received a question on how to determine this K new factor in practice. I guess this is something related to the channel, right?
Yeah, actually, it depends on the fractional Doppler. So
right.
First of all, if like the duration of the signal is large enough, so we can, like, if the fractional part is not significant, then if we can ignore the fractional part, which is maybe is not the case always in the practical cases, then the K nu is 0 simply. But if we have like it's not, the duration is not large enough, we should go for a K nu in principle. Like if we put it like to 5 or 6, it is enough, right? Because when we move away from the peak, it reduces very fast. So if we take like if we put it 6, it means that we are taking 6 elements around this subdiagonal, and then it's in, because the rest are can be considered, we can neglect, they are negligible actually.
Right. If that's the case, I have a follow-up question. Will that sacrifice some of the performance for AFDM or in terms of spectral efficiency?
Actually, yes, because at the end, the larger the C1, it means that we should increase the it would increase the overhead, right, for the channel estimation. But another thing is that actually we don't need to go for large K nu. So it's like in my simulation is like 3 or 4, and then that's it. Yeah.
Okay, thank you very much. We have another question on the page 18 where you introduce 2 parameters. One is PGI. Oh, it's already in the channel estimation part. Sorry, but like so people are asking about this the definition and the difference between PGI and the DGI here.
Yeah, actually, so it's a good question, because so when we are sending pilots, So assume that we are only sending pilot. All of these parts are 0. So the pilot, due to the channel, come to this part and also come to this part as well. So the length here and here depends on the Doppler shift, and here it depends on the Doppler shift and the maximum Doppler shift and the maximum delay shift. So this part would be related to the pilot. But what if we have data? Because this would happen to data as well. So we have this spreading for the last data and here as well. So we need to put guard for the data as well, so that the data and the data and the pilot does not have any interference. So this part, we put this part as if here we have pilot, and we put this guard here as if we have a pilot here or data, because we have a symbol and we don't want to these two parts have any interference.
I see. Right. I just want to also confirm that in OTFS we also have something the similar structure like this.
Yeah, exactly. Because the thing is that at the end we have channel, and the channel applies to all of the symbols, not only for pilot.
That's true. Yeah.
So we need to respect that.
Right. Another question related to the parameter selection is actually from Professor Zhiqiang Wei from Xi'an Jiaotong University. I'm not sure if you would like to speak for yourself, Zhiqiang, or do you prefer me to speak for you? Okay, I think he's not here at the moment. But so I think what he mentioned. Oh, okay, I think what he has mentioned is about how to select parameter C1, and is the subcarrier of the chirp has to have this full bandwidth coverage in order to make a sufficient delay resolution, or so. Right. And or is it how, yeah, it's basically, if you can clarify how this selection of C1 with respect to the delay and Doppler resolution, that would be great.
Yeah, I will. So the thing is that whatever value we choose for C1, it spans the whole band. It's like here, for example, if you look at these two figures, here C1 is 1/2n, here is 3/2n. So, but we see that, for example, look at the green chirp here and here, all of them spans the whole bandwidth. But here we have like one discontinuity, here we have three discontinuity. It would be repeated more times when it is a larger number.
Yeah.
But when we come to the when we come to the full delay Doppler representation of the channel, so this part, for example, take to account the delay I. So for delay I, now, for example, here we have 5 positions for the Dopplers. But what if the maximum Doppler is, for example, 3? Then we need 7 places for the Dopplers. So it means that if we go for the smaller C1, we don't have places for the large Doppler shifts, and then the passes would overlap with each other. So that's why we should respect the maximum Doppler we have. So in this matrix, we have enough places for all Doppler shifts, because this effective matrix that here we have, it's with the assumption that we don't have any sparsity. So we should have place for all the Dopplers within each delay.
I see. Thank you for the explanation. And another question also related to this is actually also part of my sales question. It's like sometimes the input-output relation with these parameters selected is a little bit complex because you have so many parameters that you can tune. So is there a concise or a high-level way to explain this input-output relation? And yeah, so is there a simpler way to handle that?
Actually, parameter selection actually is straightforward. The only parameter you need is like for the environment that you are in, you need to take to account the maximum Doppler shift that you want to tolerate. So you just put the maximum Doppler shift, and then you just tune C1 and C2. It's up to you. It doesn't depend on the channel, and everything is fine. So from the parameter setting point of view, this is the only parameter you need. And the complexity, so when you do the DAFT for the modulation and demodulation, you already have the effective channel, and the only thing you need to know is the mapping. For example, you should know the mapping that the component that you have here, the non-zero component that you have here, you should know that it is for delay I and the voltage Doppler that we have here. And this one is like very simple because it is like a one-to-one relation, so it is not complex at all.
Okay, thank you for the answer. Okay, I think let's now move to the channel estimation part, which I have seen that you have put quite a lot of emphasis in this talk. One question is about the comparison of the pilot overhead with AFDM and the OTFS. So, is this a general conclusion that the pilot required? Of course, like in separating the pilot symbols and the data symbols is always smaller than OTFS. And is there also something related to the special parameter selection?
No, actually, so first of all, for this comparison, we should like, for the fair comparison, we should like, if we consider so we are in an environment, we have the maximum delay and the maximum Doppler shift for these two waveforms, it is fixed. So for the AFDM, since we know the maximum Doppler shift, we tune the C1 accordingly. So with that C1, which is now fit for this environment, because for the OTFS as well, we need the maximum Doppler shift to put the guards as well.
Right.
So when we have this maximum Doppler shift and the maximum delay, then it means in this scenario, the overhead for the OTFS is almost 2 times more. Yeah, it is always the case. If we want to use this embedded pilot channel estimation, and so that we don't have any interference with the data and the pilot parts.
That's true. I agree with you. Also, we have seen some questions from the audience that people are asking, do you need to have some special treatments for fractional delay or Doppler? But I think you have covered that part during the presentation, especially in parameter selections with different like a chirp rate or something, right?
Yeah, exactly.
So, yes. Okay. So I think then we can move on to some of the high-level questions from actually particularly to the sensing part. So do you have some high-level explanation why we have some advantages for monostatic sensing comparing to OFDM?
Yeah, sure. So the thing is that it all comes because the AFDM has a chirp nature. So since we have a chirp nature, we have the feature of analog dechirping, like the FMCW radar. So in the FMCW radar also we can handle the self-interference cancellation here, but for the FMCW radar, because it is only in the analog domain, then we don't have this like modulo operation or this like wrapping or discontinuity, like this wrapping in the digital domain, I mean. So, but this feature, this analog dechirping that I mentioned, is due to the chirp nature of AFDM, which is not the case, for example, for OFDM.
I agree with you. So I guess this is actually one of the natural benefits for such a waveforms that is actually not purely frequency or purely time. So it's something in the between is good.
Exactly, because like for the sensing, we know that the chirps actually from very like long time ago, they are one of the options for the radars. And now that we have this chirp nature, we can use these features for in the ISAC scenario as well.
Yes. I have also a follow-up question in this case, because for example, if you want to use the same waveform for both sensing and communication, and you have already mentioned that for communication, you need some special way to select this the slope, for example, of the chirp. Is there a potential trade-off in the parameter selection in terms of the communication and sensing performance here?
So one thing is that, because one good part of this monostatic radar is that the length of this desired part, because like if we filter out this orange part, it means that the bandwidth that we are working on is smaller, and then we should go for a smaller sampling rate. So it is good for complexity. But if we go for a very large C1, then large C1 would increase this part. So you see, so this part would increase, and from this point of view, it would increase the complexity of it.
I see. Right. Okay. So another question is actually we go beyond the sensing is about how to achieve this in practice. So that relates to the post-shaping designs in general for AFDM. So do you have any ideas, or is there some existing work on doing the post-shaping?
Yeah, actually, we worked on that as well, which I didn't include them here. But the idea is that we can, because if we go for the continuous version, and if we have a fractional delay, then the things that we so far didn't consider here is that, for example, if you look at these chirps, you see that we have some discontinuity here in the continuous version, and also we have a discontinuity here. So this discontinuity could lead to a high variation, and it is not good for the out of band emission topic. I mean, from out of band emission point of view. So one thing we can do is that, so first, the pulse shape, the normal pulse shape that we can use for every waveform, it can be used here as well. But another thing we can use, that we can use a per section pulse shape. So, like for example, depending on the M0, we would put a pulse shape here, and then here, and then here, and here. It depends on the C1 and M0, so that we reduce the variations here in the discontinuities. So in this case, it is a new pulse shape. Actually, we have patent on that as well. So it is a new pulse shape that we can have, so that to treat these parts as well.
That sounds very interesting. If you have mentioned that there is already a pattern, so I guess like if the audience are interested in this post-shaping issues, we can have a look of that.
Yeah, actually, it is. I don't think if it is public yet, because it is filed, but it is not public. So
okay, all right. We'll just be waiting.
If anybody has a question about that, would be very happy to have a chat or talk or in email or whatever.
Okay, that's good. Right. So I have some of them personal questions, and I would also like to ask during this great opportunity. So I think there's a chirp-based signals and the OTFS and some of the new waveforms. They all have one of the special advantages in terms of the time varying channel. That is, the channel needs to be separated well with the waveform and then combined well at the receiver. So I think that AFDM and the OTFS are all some sort of a way of doing this.
Exactly.
Yeah. So in general, for these type of waveforms, I think multiple access could be a difficulty, right?
Yeah, exactly.
So is there any work on AFDM-based multiple access schemes, or how it is combined with, for example, MIMO and other stuff?
Actually, for the multiple access, what we can do is that one option is, maybe I can go here. The idea is like here, here. So this DAFT is AFDM, since we can somehow separate the users in this domain, it could work. Also, there are some works like it is a possibility to work on that as well, so that we use some sort of precoder for the AFDM. In this case, we can also have multiple users, like, because we can have the orthogonality also in the DAFT domain. Like it is like a DFT domain for OFDM, but also we can have the DAFT domain. And then in this case, if we have enough guards, then we can have sort of a multi-user or multiple access.
Right. I think that's actually one of the questions I want to make, and as always a question, it's also a question in OTFS as well, that in order to have this so-called full diversity, you need to have some of the separations between different users' data frame. So that, of course, gives you a reduced spectral efficiency, or otherwise you need to somehow deal with the interference in order to due to this like time or frequency shifts. So seems like in AFDM is also the case, right? So you need to have some guards or some like receivers to equalize the potential multi-user interference.
Yeah, this is true. Because at the end, because for all, it is a straightforward for all of them, because for all of them, at the end, we have diagonal matrix, but which is not the case for the like OTFS or AFDM as well.
That's true.
So it is not as simple as OFDM.
Okay. My own question is about this SIG transform you have mentioned. That is actually, I found it very interesting, especially for the chirp signals. I wonder, do you have any further any further information on the ambiguity function of AFDM waveforms, or in general chirp waveforms with respect to the SIG transform?
Yeah, actually, for the ambiguity function, we investigated that as well. So the thing is that for the ambiguity function, which also gives us like somehow the feeling for the input-output relation, because it has the delay and Doppler information in it.
Yeah.
So its performance also depends on the C1. So like if for example we take an AFDM chirp and then we look at the ambiguity function of this chirp, we can see that we would have a main peak at the zero delay and Doppler, and then depending on the value of the C1, around this peak would be zero. So we have a good peak, and then it could be around this peak would be zero, but we would have another peaks, and this is actually set how we should set the C1 in one hand. On the other hand, is that how we can go the maximum. It says how we should tune the maximum delay and the maximum Doppler shift.
Yeah, I think that's a really good point. And a follow-up question from me is actually, we know that in SIG transform, there are supposed to be some quasi-periodicity exists. So I know that you have mentioned in chirp domain there are also some periodicities, but I would like to know how this is translated in the SIG transform. So is it also a periodic signal in the SIG domain? I remember you have mentioned it's a finite response in SIG transform, right?
Yes. So actually, I think it should have a kind of periodicity, but I don't know how this periodicity would be, because like even for the AFDM for the DAFT transform, we don't have a normal periodicity. We have as I said, we have a chirp periodicity. Here, I think we should have some kind of periodicity, but I don't know how the periodicity would be.
I agree. Okay, so if we have some periodicity in the SIG domain, then it will turns out we are facing this so-called ambiguity issue in sensing. That means you cannot distinguish delay or Doppler if they can have a very long support. So is that also the case for AFDM?
Actually, I cannot say with 100% sure here, but because at the end, all of them translate to one thing. So it's like at the end we have the ambiguity function, and for the ambiguity function of AFDM, what I can say is that its behavior, as I said, depends on the C1 and the maximum delay and Doppler shift. So we can be at some point from like a delay, if a delay is larger than a L max, or if the Doppler shift is larger than the maximum Doppler shift, then we would have ambiguity as well.
Okay, I think the one last question for me is actually in OTFS or in OFDM, people are emphasizing some of the properties of the channel. For example, the channel needs to be underspread. However, I don't think that is something being considered very specifically for AFDM, right?
No, actually, no.
Mm-hmm.
So it's like so far we like as I mentioned for the
Yep.
in general it is for the LTV channels, but if we have some assumption, we can have another features like if, for example, we in general for AFDM, for example, if we don't have Doppler at all, then the C1 should be the 1/2n, or it's like the OCDM. It should be OCDM. But if in such case we increase C1, we can have other advantages, as I said, like we can go for the sub-Nyquist radar. But apart from that, no, we don't have such.
Okay, I think that's actually one of the very interesting part, because we know that in some cases, for example, in underwater communication, the channel is overspread, and so far we do not have some very good waveforms to deal with it. But as you mentioned, that AFDM may be a promising solution there, and I'll be interested in knowing more about this
This
technology.
could be a good way to go. Yeah,
Okay.
exactly.
Okay, great. Thank you so much for today's presentation. And
Thank you for having me.
and I think we do not have time to cover all the specific questions, but if someone has further questions, you can send me an email, then I'll follow up to Ali in a good time.
Sure.
Yeah,
Sure,
and
sure.
also, thank you. And also, the presentation recordings will be uploaded on YouTube and Bilibili. So if you have any, if you are interested in this, you can check it out later. Okay.
Yeah. Do you have 1 minute?
Oh, yes, please.
Sorry,
Please,
Ali.
yeah, sorry. Yeah, please.
Sorry, I think I have a small question, if you don't mind to ask.
Sure.
Actually, Ali is Jin Hong here from University of New South Wales, Sydney, Australia. Very interesting talk. I'm reading your papers. So one question is from our group. I think Chen put it there. Is could you go into a bit more detail on how to obtain a continuous form of AFDM waveform at the transmitter side? Do we need to use the continuous chirp when applying AFDM to ISAC? Actually, it's two parts of a question. Thank you.
Yeah, sure. So yeah, this is a good question, because at the beginning, when I wanted to compute it, I thought it is straightforward, but at the end I found that it is not that much straightforward. The thing is that since we have, maybe I can share again. Sorry.
That would be much appreciated. Thank you.
So if we look at the chirp here, for example, one of each of them, it doesn't matter. So we have this wrapping here for each chirp. So the chirp should not surpass the bandwidths. So it should come here, and then it starting from 0 frequency, comes to bandwidth, then come back to 0 frequency, come back. This should be repeated. But so what we did is that we should start from the discrete domain, and then there are two options here. One, we can go for we can oversample the signal with the going to the frequency domain, putting the edges to the 0, and then coming back to the time domain. So in this case, we oversample the signal. So this could be considered as one solution, but the thing is that here we would have, instead of discontinuity, which is the perfect chirp has this discontinuity, they have high variations. It's not discontinuity. So if we go for this way, but another thing that we can do, it is my integers as well. So we just write the continuous version, but by looking at the instantaneous frequency. So when the instantaneous frequency reaches the bandwidth, or 1/delta t, then we should come back, we should define a function so that when it reaches this value, it should come back to the 0 frequency and what have you. So in this way, then you would have the continuous version of the chirp puzzle.
Thank you. I think this may be, you may have this out of band emission if you do such a way, or I mean, it's a question I don't. Yeah,
this could be. This is because at the end If these points are triggered, then it means that we have discontinuity. And if we have discontinuity, yeah, it would increase the out-of-band emission. But with the pulse shape that I explained, we can reduce this effect as well.
Okay, that means with your pattern and the pulse shaping, this problem can be solved. That means there's a way to, okay. So with that one is out of band is completely expressed, or it is still have some excessive out of band emission?
With the pulse shape, we can have good performance.
Okay. Okay. Thank you.
You're welcome.
Thank you very much for your talk.
You're welcome.
Thank you, Professor Yuan, and thank you, Ali, for answering the question again. Yeah, I guess.
Thank you, Professor Yang.
You are more than welcome. Yeah, I guess that's finished our today's presentation. And if there are any follow-up questions, please send me an email, and I'll forward to Ali, and we can have a answering as well, right? Okay, all right. Thank you all for joining us today, and see you guys next time.
Thank you, everyone.
Thank you.
Thank you.
Bye-bye.
Goodbye.